Hi, my name is Stephen Hua, and this is Lab 3, the black hole, for Physics 2211. This lab is going to be about the forces that a black hole exerts on cosmic objects, specifically a star in this model. The purpose of this is when we calculate the net force components from the motion of the star orbiting the black hole, we can determine the mass of the black hole. The important concepts that I used in this lab were the momentum principle, Newton's second law, and Newton's law of universal gravitation. The equation of the rate of change is the momentum of the parallel and perpendicular components. It shows the total net force based on Newton's second law. The next equations show that the parallel and perpendicular components and the parallel components points parallel and in the same direction of the motion's object, and the perpendicular component points perpendicular to the object and points towards the center. The next concept that I used is Newton's law of universal gravitation. The force of gravity acting on a pair of objects is directly proportional to the mass of the objects and inversely proportional to the distance between them. And the reason that's important is when we're calculating the mass of the black hole from the equation, we can set the force of gravity equal to the net force from the computational model and solve for the mass of the black hole. So this is my model using GlowScript. As you can see, the yellow sphere is the star within our system, the black dot is the black hole within our system, and the orange arrow is the magnitude and direction of F net, while the magenta arrow is the parallel arrow and the sign is the perpendicular arrow. And as you can see within the model, the forces grow as the star gets closer to the black hole, and the arrows grow significantly shrink smaller as they get away from the black hole. So now looking at our code, our GlowScript code, we can see that the initialization setup is where I changed my C to be the email, the mass of the star to be 2.0 e to the 30th, which is 2.0 times 10 to the 30th power, delta T to 86,400 seconds, which is the conversion of 1 Earth day to seconds. And then this slide, the code specifically just runs over and over and updates the components of the velocity for the x and y components. And that's based on the seed that was created from my email. And this is the most important slide about the code. So within the net force calculations, as you can see, I use the formulas from our important concepts, specifically the momentum principle. And we set the momentum vectors equal to the mass of the star multiplied by the initial velocity or the final velocity. And then I found the change in velocity and change in momentum. I used the momentum principle to find the rate of change of the momentum, and using Newton's second law, I can set F net equal to the rate of change of the momentum. And then I found P hat and used the magnitude of the initial and final momentums and subtracted it from each other and then divided by the change in time to get the magnitude of the parallel change of momentum. Then multiplied it by the unit vector to get the rate of change of the parallel momentum and set it equal to the force. Then we can use subtraction to get the perpendicular components. When we find all F nets for the data points, we can calculate the mass of the black hole. When using Newton's law of universal gravitation, we can solve for the mass of the black hole, and we use 6.67 to the power of negative 11 or times 10 to the power of negative 11 as the gravitational constant. Doing this, I found the mass of the black hole to be 8.75 times 10 to the 33 kilograms, or 400 solar masses approximately, and which is reasonable for black holes because they can range from single digit solar masses to billions of solar masses. And what does this mean? How is the net force different from the rate of change of momentum? The net force is what causes the change of momentum. While numerically they are the same, the net force changes in velocity, which leads to the change of momentum, and which is why they're not the same thing. What if? What if the black hole was swapped out for a different black hole located at the origin and the star's motion did not change? The star's motion decides the mass of the black hole, so if the star's motion didn't change, then it wouldn't be possible to find a new mass of the black hole. And that's the end of the lab.